today. Leo, can you take a look? Has this been start? Oh, yes, okay. Okay, so let's start. Last week, when we review vectors, and some students write a private note to me, Professor, well, why we still learn vectors, right? Still learn, so he must thought, you see, he learned in high school, right? And then also maybe some other class in CHK, and why we need to learn vector again. You see, then I answer him, are you sure you learn very well? Okay. See, I learned EM theory 40 years ago. Then I'm still learning. Okay. You see, different time, you'll have a different understanding, different depths to understand, right? And also, we are talking about more specific application. And I try to train our students to think in a way, not in a number, try to think a problem in a way of a formula, okay? Or even formula, okay? And that gave us more abstract, more logic, more general solution, okay? So that is why you see we still need to discuss vectors. And then, so I gave the assignment one that I received some of the feedback from students saying under quite high pressure. And then my reply is, my job is keep you thinking, okay? And if I give you a problem, and then I immediately give you the answer, what I'm doing, right? So I don't want to have a spoon feed our student. That's not good for our student, right? Okay, let's back to our material today. We continue the discussion of coordinate. Okay, last week we briefly reviewed Cartesian coordinate, and now let's continue cylindrical coordinate, and then later on spherical coordinate. So these three coordinates are orthogonal coordinate systems, and we are using very frequently, and particularly for spherical coordinate. And when we describe antenna radiation property, we always use spherical coordinate system. Okay, if you come to the industry, if you look at the antenna specification, if you don't understand spherical coordinate, you get lost. All right, okay. Let's say for cylindrical coordinate, again, we need to define three surfaces. Okay, the intersect of three surfaces define a unique point. Okay, define unique point. So these three surfaces is one is Z, okay, Z equal to a constant. Okay, then we have angle phi equal to a constant. Okay, and then this surface, can you see my shared screen? My PowerPoint? Sophie, can you see my PowerPoint?
Yes.
Okay, so this define the radius r equal to a constant. Okay, so once we define these three surfaces, right, then we get unique. Then we get the unique point defined in a three-dimensional coordinate. Okay, so when we define these three variables, so we always have a range of the variables. So those range extend infinitely large space, right? So here we introduce three unit vectors, r, phi, and z. You see, here we use triangular hat, okay, to define this is a unit length, okay? We use unit length, you see, from time to time, right? And according to the definition of cross multiplication of two vectors, then this is a way that define a right-hand orthogonal coordinate system, right? So if you have R, right, and then cross phi, the thumb point to the Z direction, okay, or phi cross Z define R direction, okay. So this is unique, and everywhere on the Earth, all right. Also, because this is a unit vector, so we have these relations, okay, and this means orthogonal. Okay, that means orthogonal, right? Similar to the Cartesian coordinate system, once you define the unit vector r, phi, and z, and any vector in that space, you can have a projection on these three orthogonal coordinate system. The projection we call the component, okay? This projection we call the component also. Right, so that is a component in R, phi, and Z component, right? And again, we can define unit length. Now we should appreciate after we finish the assignment one. The differential length is a very useful quantity, right? We use differential length, we can define a normal direction of a surface. We can use differential length to define differential area. Then we can define differential volume in orthogonal coordinate system, right? So if you ask me, what is the first principle? Differential length is the first principle, right? Similar to what we did in Cartesian coordinate system, in cylindrical coordinate system, we have a different way to express differential length. That's also in terms of this unit coordinate vectors, okay, the projection, right? But however, that movement is a change along the R direction. This is along the R direction, okay, R direction, phi direction. But when we deal with phi direction, okay, dl phi, so we know this is equal to R times d phi, right? Because the angle in radians, right, and then times the radius, and then dz. And so if give you a specific surface, ask you to find the differential length at a certain location, the only thing we need to do is to find the relation between dl, d phi, and the dz, right? If you find these three relations and 3 differential quantity in terms of 1 differential quantity. Then you have done, right? Okay. So from a given specific surface, you can use that surface to take derivativity. Then you can find these relations. Okay. And once we know the differential length, okay, once we know the differential length, we need to define the differential area. So look at the very, very small volume defined in cylindrical coordinate. Then we have one surface. This surface, the normal direction is in dr, right? The normal direction is dr. So we call this surface is called DSR. So its area is obvious, right? So this length is r times d phi, right? And this height is dz. So the total area is this, right? Total area. So the same as the other 2 small differential surface, one point to the z direction. Okay, then we know the length of the arch, we know the length of dr. So this is the differential area of this surface, right? This surface. So the same as this surface. This is easy because dr times dz, right? So once you know the surface, then you know the differential volume. Okay, you know differential volume, right? And then because we understand, once we understand this, we are much easier to make to formulate our problem, electromagnetic problem, using calculus, right? Okay, from time to time we need to convert from one coordinate to another coordinate. Okay, one coordinate, for example, so far we have learned is Cartesian coordinate, and then the conversion from Cartesian coordinate to cylindrical coordinate, then it's pretty straightforward. We just find the relevant projection. For example, now we have a point in cylindrical coordinate system. Okay, we like to convert it into cylindrical, Cartesian coordinate system. What I do is, okay, I found the projection of r component to x-axis and to y-axis, right? So this is, if this is phi, so this is phi, right? And then this is phi, all right? Okay. So let's look at the r. Let's look at the r component. R component, we have a projection on x-axis. So this basically is if this is a unit length, right? Then that time sine phi, right? Oh, sorry, not sine, cosine, right? This is a projection, right? Then the projection to y-axis, this is a AR times then this is a projection on y-axis, right? AR, then this is sine phi, right? This is sine phi. So AR is a sine phi. But okay, so that means, okay, let's say how about phi component? The phi component, the projection on x-axis equal to minus a phi times sine phi. The reason is a minus is, if you look at the direction, is opposite to the x-axis, right? So that is what we have is, if we look at the r component and the phi component, how much contribute to the x-axis? We have this form, right? So this times this, okay? This times this. We have a cosine phi times AR minus sine phi times A phi, right? And then if we look at the y-axis, both R component and the phi component contribute positive component. So that's why you see we add, this is sine phi, and also if you look at this projection, this is A phi times cosine phi, right? Then that axis is the same. Then we only discuss one case, okay? We only discuss it. So you don't need to remember how to convert from one another. If you couldn't figure out or couldn't remember, take less than 1 minute. You can find their relation, okay? Then you can write this matrix. Once you have this matrix, okay, this is a basic, you can treat it like dictionary, right? I convert English into Chinese. This is my English to Chinese dictionary, right? Okay, then if you like to find the other way around, okay, Chinese to English dictionary, easy, okay? You just take an invert of this matrix, then you find the coordinate in symmetric coordinate system, and then you translate Chinese into English, right? Then we said we should get used to deal with formulas, right? And then once we know the coordinate system very well, and then from time to time, you see, we need to find more conveniently, okay, we need to find a vector expression for general description. Say, for example, I have a point. This point I describe in cylindrical coordinate system is convenient because I keep the same radius r, and for arbitrary phi, and on a point, okay, on a point with z equal to 0, say. Okay, then I have another point located along the z-axis I call point Q. Then I need to tell me what is the unit vector from Q point to P. So in this case, I know, okay, if I can find the vector QP, okay, and then I divide its length, this is my unit vector, okay? Then to find the QP, and the QP is a vector from from Q point to P. Okay, then that reminds me is, if I can find the two vector, if this is a vector A, if this is a vector B, okay, then vector C equal to vector A minus a vector B, right? So graphically, it's very clear. Then how to write vector A? Vector A is a vector, sorry, PO vector, right? Then in this case is just RAR. This is vector because defined naturally by cylindrical coordinate systems. Now you see the convenience to have the convenience to have this vector, right? And then to have cylindrical coordinate system, right? And also the point B, the vector B basically is a QO. It's just, if this is the length is h, the height is h, okay? So the h, that, right? Then the QP, okay, is vector A minus vector B, right? So is RAR minus H. Now you get everything, right? Then because you see, because the R and the Z direction are orthogonal, so we can use Paragasin theorem, 勾股弦定理, right? Then we can find the magnitude, okay? So that is a very convenient way. If we introduce coordinate system, we use coordinate system correctly, okay? And similarly to spherical coordinate system, we defined by 3 surfaces, okay? Also 3 surfaces. One surface is theta, so that looks like a cone, like an ice cream cone, right? So this surface is a theta equal to constant, and we have a phi equal to constant. So this is a r equal to constant. So this is like a sphere, right? This is like a sphere. Then again, we have a cutting plane. This cutting plane, we define this is a cutting plane. So this cutting plane is phi equal to constant. So we define right hand by right hand the orthogonal unit vector r, theta, and phi, right? And we can have a projection, okay? Then we can define a norm, or you call the magnitude of a vector defined by these 3 unit vectors, okay? And then any point, any position vector define any point on in this 3-dimensional space, we can define using this. Okay, it's so elegant. Just using one unit vector, I can define it. Okay, I can define it. And again, we can define the unit length. Okay, unit length. From unit length, we can define a unit volume, a unit area, and a unit volume. All right. And also, we can have a translation dictionary. Okay, then we can convert from one coordinate system to another coordinate system. So I should skip it. Right. Then using spherical coordinate system, whenever you think that is most convenient to use, right? For example, if we like to find the total area over this a section of sphere, okay, then with defined by two constant theta. So the theta is larger than 0, smaller than 60 degree, 30 and 60 degree, right? And the phi is defined from 0 to 2 pi, all right? And the r is constant. Okay, r is a constant. Let's find the total area. Okay, to find the total area, then you say this, if we can find a differential area over this differential area is really the DSR, right? The DSR. This DSR, let's back to this. DSR you look at this. Let me emphasize this. This is our DSR, okay? Then we know, okay, for differential area of our problem, okay, this equal to r square, okay, r square times sine theta, right, times sine theta, times d theta d phi. Okay, then we also, this is a differential area. We just collect all the d theta and the d phi in this range, we got surface. So that is why we get integration, right? This is how we formulate problem. Why we are so interested in differential area, differential length, differential volume. Okay. Now, rest of it is the high school stuff. We don't need to discuss, right? Okay. We discuss how to formulate the problem. Okay. For those things, suppose it's not our job, is that the computer's job. All right. And at least directions, okay, dictionaries in next, okay. This is dictionaries we can convert, right, from one coordinate system to another coordinate system. Okay, this is from Cartesian to cylindrical to Cartesian. We already discussed it, right? Right, we already discussed, and then you can find out by yourself. You see, from Cartesian to spherical to Cartesian, right? And then also you can convert from cylindrical to spherical and spherical to cylindrical. So that's all the dictionary is. You don't need to remember. Okay, if we really need it in examination, I will give to you. But however, you know how we find it. So in case if you really need, and then you can take 1 or 2 minutes, you can find it. And also, this page summarizes the basic property, how we define these 3 important orthogonal coordinate systems by right hand. Okay, how the unit vector is defined. Okay, then also to conduct the vector product in different coordinate systems that result different formulations, but that pretty much looks the same, right? You see, if we can remember for Cartesian coordinate system for A cross B, and this looks very similar. Okay, very similar. But however, remember the you see, we put R, phi, Z, right? And also for spherical coordinate system, it's the same thing. So, but you see the different length and different volume, that different area, and that definition really determined by how we define differential length. If you can remember how differential length is generated, okay, then it's not surprised we can find the differential area and differential volume. Okay. All right, okay, so that is a review of coordinate system. Let's back to our real business. Okay, our real business is how we our real business is talk about the field, right? Our real business talk about the field. And let's look at the static electrical field. Static means the field doesn't change with time. This is what we learned in high school. Then if we put a positive charge, we know the electrical field will be go out, right? And then because from positive charge to negative charge, and where the negative charge is at infinity, okay, at infinity. So this is then we can say we have so-called field lines, okay, and similarly to a negative charge, we have the electric field go, you see, ended at negative charge, okay, from positive charge. But in this case, we don't know where the positive charge is, okay. We also assume at the infinity, okay, and uniformly distributed, okay. But when you put one positive charge, one negative charge close, then we can see the field line change. And then for each line, okay, for each line, we represent the field strength is the same magnitude, but in the space that the direction changes. Okay, so along each line, the field magnitude we consider is the same. Okay, so that is what we call field line. Okay, we call field line. And we also have a field, scalar field. Okay, so what is a field? A field is a variable that change with the positions. Okay, temperature, not look at the globally. You see, this obviously is different. The temperature in Hong Kong and even temperature in Shenzhen, right, is different. Even the temperature inside my office at different location is different. Okay, different location is different. Then not mentioning the globally, right? Do you know what caused that change, the difference? What caused the difference? What caused the difference? Let's say if the temperature in my office, different locations different. Why it is different? Have you ever think about? Sure, you see my office temperature change. If I turn on or turn off the air conditioner, temperature is different. Yes, I can say air conditioner is my source that affect my temperature in my office. But also, if you think my office, if my office is bigger, sure, I wish I have a much larger office, right? Everybody like to have a large office. Then do you think the temperature will change? Of course, it will change, right? So the temperature change because my environment to change. Or if I use more academic terminology, is the boundary change or the boundary condition change, right? So similarly, you see a gravity is a field, okay? That is a vector field. Then we have a direction. And the static magnetic field, that is a vector field. Also, we can draw a field line. Right? So I'm going to give assignment is, can you write a program to draw this field line if giving you a field? You see, because we like to visualize the field from time to time, right? We like to visualize the field from time to time. You see, right now, those joints, you can say, oh, Professor, you just draw it arbitrarily, okay, by hand. Sure, I have no time to do the calculation, okay? But I can give you a task. I let you to have a more scientific way to draw a field line, okay? Okay, before we talk about this, let's make a summary, okay? What I mentioned many different type of fields. What are they in common? What are in common? First, they must have a source. Say, if you have a charge, you have electrical field. If you have a current flowing along a wire, we have a magnetic field. This is Ampere's law, right? Okay. And then we must have a source. Okay, that's one thing. And also, what determines the distribution? Say, for example, if you have magnetic field, if you put another magnet, nail this conductor wire, do you think the field is still running around the wire like a circle? No, right? So that will be changed because your boundary condition changed. So we must deal with the boundary condition. When we talk about a field, we must deal with boundary condition. Okay. Then we also have a governing equation that the field must follow this governing equation. This is not an easy job. I said the governing equation for electromagnetic field are one, Maxwell equations. And the Maxwell equation is the greatest equation in the world, even greater than Einstein's equation. Because Einstein's equation is inspired from Maxwell equations. Right? Okay. I will put a short video produced by BBC many years ago. It tells you the story. Okay, how you say Faraday and the Maxwell, how they you say they communicate, and then how this Maxwell equation was invented. Okay, now the governing equation for different field, we have different governing equation. Oh, okay, I have to be catch. And later on, you will see different field because of the governing equation. You have a unique identity. You have a unique identity. Okay, this unique identity, for example, magnetic field, you don't have beginning and end at two different points. These 2 points must be always at the same point. That means the line, the field line, always a closed form. And on the other hand, electrical field always have two ends, two different points. So electrical field never be in a closed loop. Okay, this is identity. This is identity, right? Okay, now let's talk about how to find a streamline, or we call flux line, or we call field lines. They're same thing. Okay, same thing. Those lines are vector field. We just mentioned what is a field. A field is a vector. Let's talk about the vector now. Okay, the vector field is a function of a position. Okay, so that means it's a 3 component of a vector is a function of a position x, y, z, and also a function of time. Okay, let's ignore time for the time being, right? So it's a function of time, location. Then what we like to find is, okay, what we like to find, oh, I missed the one word I added last night, because even though this class I taught more than 20 years, and before every lecture I still spend time to read my notes, and in my notes post-it I should add this word. Okay, I emphasize this line along each curve that represents the field of the same magnitude. Okay, the same magnitude. But however, this line must be, the field must be tangential to the curve at that point. Okay, this is the definition of our field line. Okay, so because this is tangential, that means in the same direction as our dl, differential length. So dl is important, right? dl stands for what? Is tangential direction of a curve at a particular point. Okay, and this dl in the same direction as my field direction. That means I must satisfy this relation. If you have 2 vectors in parallel, you must have this relation. They are component, corresponding component in the same ratio. All right, equal to the same constant. All right. Okay, equal to the same constant. Okay, having had this, then if you're solving this, you can solve dl of the curve, then you can draw this for a given point magnitude. So for example, we have circular disk. We have a circular disk. This circular disk spin, rotating at the central axis at a constant velocity omega. This is angular velocity. Okay, then let's draw, because this is there is angular speed, right? So speed is a vector. Let's draw this field line. Okay, the field line. So first of all, let me write this vector. Even though this vector in phi direction, the force applied in the speed is in phi direction, I write it in xy direction. So that is simple projection. Or you can find the dictionary. Okay, this dictionary is from English to Chinese, right? English to Chinese dictionary. Then you can convert from cylindrical coordinate system into rectangular coordinate system, right? Or you can find your own way to take a projection, right? Then you get a vector in terms of x and y. Then you get a differentiation. Then you get differential equations. This is differential equation, right? Because these 2 vectors in parallel. Then you multiply y to this side, x to this side, then you have what? You have x dx plus y dy equal to a constant, right? Oh, sorry, here, Then you do integration. What that means? This means dx squared plus dy squared, right? Equal to constant, right? Then that means x squared plus y squared equal to constant. That is circle. Okay, that is circle. Then they give you a very simple example. Then we can find. Then for a given r, for given constant, that means distance r, you can find this field line. And later on, we can find more sophisticated problem. Okay. So good timing. We can ask one question. So after class, I will be here for a while. So if you like to talk to me, so after class, you are very welcome. So any questions? Okay, very good. So we have 56 involvement. So I will keep record my lecture. Okay, if no questions, so let's end the class. Thank you.